popular and brought so many of you here. So thank you very much.
Thank you. Okay, so let me just go through real quick what I want to talk about. So the idea is just to talk about time integrators for, I mean, I kind of use this title of AMR, and it's really not, I mean, I kind of try to fit into the program of adaptive multiscale, but we're looking at these time integrators anyway, and I'll tell you what these guys are. So collaborators, real quick, this work is in conjunction with Emil Constantinescu at Argonne National Lab. He's quite knowledgeable in all these time integration stuff. You know, that's pretty much all he works on. So it's kind of a nice counterpart because I mostly work on spatial discretization. He works in time, so we've kind of come and met halfway somehow. And then Patrick Mugg, who was my master's student who worked on multi-rate methods, I'll show some of his stuff here today. Okay. So how am I going to motivate this? Is thinking about AMR, and perhaps one thing you can think about is say that the I guess trying to increase the efficiency of GFD models using fewer degrees of freedom than uniform high resolution, right? That would be what one motivation for using AMR. The other one would be to solve problems previously not feasible. So an example that I have here is let's say this rising thermal bubble. I guess I do have the movie so I can play it. You've seen it already. But the idea is, you know, imagine trying to do this in time where you have some time integration method. You can see that these smaller cells here are going to dictate, if you're using an implicit-explicit method, they're going to dictate the time step restriction. Of course, if you're using a fully implicit method, that's not the case, but then there's other issues involved with that, which I won't talk about here. So what I meant to say here is that the finest grid resolution will dominate the maximum allowable time step, right? So here's an XT diagram, here's X and here's T. And so what I'm saying is, imagine if you have these delta X cells, and then you have some small cells, like I just showed you in the movie, that are delta X over 2. Okay? Then imagine if you're doing a constant time step delta T everywhere, then of course these guys here are going to hit the stability limit before these element cells here, right? Because stuff is going to be going through these cells very quickly. So then the question is, you have to somehow either divide delta T by 2 or do something to handle that. And if you don't do anything special, then you can still do implicit-explicit methods and globally make your time step a little smaller, but you're not really taking full advantage of AMR. And that's what I'm sticking to right now. Okay, so possible time integration strategies. We've looked at a few of them. I won't say that we're well-versed in all of them. We primarily work in IMEX methods. We have some extrapolation methods in our codes, and I'll tell you about these. And then we started looking at multi-rate methods when my master's student did his thesis on this stuff. So let me talk to you first about implicit-explicit methods. We've seen these already. We've seen them yesterday by Sarah. You just saw them by Dale. And I'm sure you'll hear more of these in the rest of this program. But let's say you had this, the QDT equals S of Q, where S is some spatial discretization of your PDE. So now you have a system of ODEs that you need to solve. And Dale talked about that. You have a linear operator over here, and you have say you have a nonlinear operator, but it's slow-moving waves, and this linear operator that has fast-moving waves. We rearrange this, and what we end up solving for is this implicit problem on the left-hand side, but the problem is the right-hand side. The right-hand side has it's explicit. So let's say you have your wind velocities in there. So your time step has to be your time step will be restricted by your spacing because this guy here is explicit. So in other words, if you're using some explicit method that has a small stability region, then you're going to be in trouble. Question? Yeah, Rob.
Because I just want to catch all these talk. When you always talk about fast and slow, you mean really? Do you really mean that the linear part has fast all the way down to slow, whereas the other one has mainly slow?
This
because
guy.
It's like a diffusion.
So let's assume here. Okay, let's say it's Euler, right? So let's say I only have acoustic waves here, and I have everything else in here.
Only acoustic.
Yeah, let's say I only have acoustic waves in there.
Okay, but the model problems we saw before, they have usually kind of the whole spectrum, and that's why you want to make the stability region to be the whole length of the.
And you can. So you certainly, in this case here, you can have either. Dale, do you want to say something? I was going to say you can have either acoustic waves and gravity waves, which is what we do. But I mean, to make it simple, think of it as in terms of acoustic waves.
But
and
the reason
linear
you
part.
try to get this stability over the whole thing is because you usually can't expect that it's
You have multiple scales.
Okay.
You have
Yeah.
multiple scales. That's right.
But some of the acoustic modes can be low frequency.
That's
Some of
All
the-
wave numbers.
That's right.
right. That's what we're just saying.
Yeah. Okay. Now understood.
Okay, so let me tell you just a kind of a big picture slide of IMAX methods. We've studied a large class of these methods, and we've looked at these multi-step methods. We've looked at single-step multi-stage methods, which are the RK families, and we find these methods to produce the best results. And what I mean by the best results is in terms of solution accuracy, we've looked at problems with self-conversion studies. I'll show you some of those in a minute. And what we see is that these methods have minimal dissipation error, and that dissipation that I'm talking about is attributed to the time integrator. The other nice thing about IMX RK methods is that adaptive time stepping is very straightforward. You know how it is with any kind of single step method, changing the time step is not an issue. In multi-step methods, you can still do it, of course, but you have to work it out very carefully. The other thing about it is that to try to find astable methods, I guess I should be pointing with this guy here, you can't find astable methods for multi-step methods beyond order 2. Right? You can see them in the BDFs and the Adams methods that they're only astable for k less than or equal to 2. With IMAX methods, you can extend that to larger orders of accuracy. So let me talk to you about the kinds of methods that we've been looking at. You know, it's these IMAX additive RK methods, which we call IMAX ARC or ARK. And here's how they work. So let's say you have your PDE, you've discretized it in space on the right-hand side. Now you have a system of ODs. We have a nonlinear part and a linear part. And then the idea is that we split up the problem into, so here is, you solve this problem with some set of coefficients, which is the nonlinear explicit part, and you solve this problem here with a different set of coefficients, which are the linear implicit part. And of course, these big Q's here are your stage value. So what these Q's you can think about is, let's say you're trying to go through your domain in time with delta t being the thickness of these yellow lines here, and then these stages here are sort of intermediate values between those time levels. And if you look at the Butcher tableaus, which is the way we typically write these IMX methods or RK methods, here is the tableau for the explicit part, and here is the tableau for the implicit part. Now, some properties that we like about these IMX ARK methods are the following. Why are they called additive? The reason why they're called additive is because they use standard explicit RK parts. So in other words, this part of the tableau here is a standard explicit RK method that you use, second order, third order, fourth order. You'll recognize that. These methods, and then we augment it with an implicit part, which is this one over here. Typically, you hear about these methods called DIRC, diagonal implicit, and unfortunately, you have to do one implicit solve per stage. So the goal is always to try to find an IMX method that has that's of certain order, that has fewer implicit stages. The one nice thing about these ARKs is that the diagonal coefficients are the same. In other words, this blue box here, let me just tell you what these guys are. If you look at this line, this blue box here, these terms here are the last guy in here. So this is what makes the problem implicit, because you'll see that when j here is equal to I, right? So this is q superscript I, is the same as this guy over here. So you have to move this term to the left-hand side and solve that implicit problem. What turns out is that in these methods, these AIJs, right, along this diagonally, A22, A33, all exactly the same coefficient. So in other words, if you're doing a heavy scheme, when you're doing only the implicit part is only the vertical part is implicit, you only invert that matrix once, and you keep it, and you keep using it. So in other words, at every column, you only invert one matrix, even though you're going through multiple stages. It's a really nice advantage. Okay. Implementation issues. How you actually implement these guys is, again, if I rewrite my original operator on the right-hand side, let's call it R now, and I subtract it by L, I call this my non-stiff part. and LQ is a stiff part. Now you see that what happens here is I say that R is a function of Q, whereas now I'm saying L times Q. So I could have said L is a function of Q, but since this is linear, I can just say L times Q. And then it turns out that if you go through this derivation here, which we have in this paper, this CISC paper here, it turns out that you can rewrite the IMEX RK methods exactly like you can a Crank-Nicholson method, a BDF method, any multi-step method is very simple notation that is classical of semi-implicit methods. So you can rewrite the IMEX RK method exactly in the same way if you go through these details here. And I don't want to dwell on this because it'll take some time, but I'd be happy to show you the paper. Okay, one of the things we did in this paper that I'm talking about is we went through and we developed a new second order partition IMEX multi-stage method. And we played around with the explicit parts. Dale was talking about extending the stability region of the explicit part. That's exactly the kinds of things we've also been doing with these ARK methods. And we came up with about 8 different kinds of stability regions. And then we tried them, right? Some of them look great on paper, and then we put them in our codes, and we found that there was a clear winner, and then we eliminated the rest of them. And it's unclear why the analysis that we have that told us that certain methods were better, it's unclear to us yet. Maybe it's the kind of problems we did, but there's definitely clear winners, and I'll show you some of this in a minute. Okay, and so the idea is, well, all we did here is, I'm only showing you the explicit Butcher tableau. Here's the values we came up with, and you can actually see that you have, this is an explicit stability region. The imaginary axis is coming along right here. You can't see it. But anyway, so if you think about it, if you have a hyperbolic problem, your eigenvalue is going to be right along here. If you're using a DG method, their eigenvalues would be a little bit inside in the imaginary, in the left-hand side plane, but for the most part, these methods look pretty much the same. And let's see, the stuff that we did to build these methods really built on the work by Butcher and Chen in 2000, and then we just made some modifications and came up with a new explicit parts for this ARK2.
So in the one on the left, is the imaginary axis just tangent to that side of the
this guy here?
Or you're actually damping a little bit of...
No, it's right on here.
Yeah.
Yeah, it's a terrible plot. I'm sorry. I'll show it to you in the paper.
Okay.
Yeah. And then here's some examples of what we did. So we ran a lot of these test cases. I'm only going to show you one here, but we ran a lot of test cases where we actually have, for example, let me explain to you what these plots are. I showed them the first talk I gave here. So on the left, on the vertical panel is L2 error. Again, this is a self-convergent study. And then on the right, on the horizontal panel, on the horizontal axis is Courant number, which is a proxy for delta t. And we went through a bunch of methods, you know, a third order 5-stage explicit method, one of the Adams methods, our BDF methods, and then all these ARKs. We did them in heavy, that 1D means heavy, and 3D means you're solving the full implicit explicit problem in 3 dimensions. And what you see is that the red, black, and green lines are the second order methods in our study. And you see that they're not all created equal. You know, all second order methods are not the same. It turns out that this ARK2 that we've been playing with looks pretty good, but of course, if you look at the higher order methods, they in fact fit the theoretical convergence rate. So for example, this light blue line here is the fourth order method. You see that it does have the same convergence rate as the fourth order methods. And if you look at L2 error versus wall clock time for this problem, you see that again, the green line here, if you can see it, it's better than the red and black lines. Okay, maybe not by much. And then if you go to higher order, you really see the difference with, for example, the fourth order methods. And so this solid blue line is the heavy method. The dashed lines are the 3D methods. Okay, so what we see from this is that we really do get a lot. We get something for high order. We're getting a better error with respect to wall clock time, especially if you think about as you increase, if you're looking for a threshold of smaller and smaller error. If you don't care so much, then you know everything. It's kind of a wash up here if you're looking for a large error. And one of the things that we found interesting was if you look at also the mass and energy loss of these methods, right? The methods that we use, the spatial discretization method, should conserve mass, but they don't need to conserve energy because we're not writing them in energy conservation form. However, you should see that they conserve energy up to time truncation. And one thing that you see is that, so here is basically 10 to the minus 16, this line down here. All of the ARK methods are all sit over here. Oh, sorry, all the RK methods sit up there, including the RK35 and all the ARK methods all sit at basically 10 to the minus 15th. But one thing that's interesting is that the BDF and the Adams methods are not conserving mass for us, and this is still something we're looking into. In terms of energy, okay, we're not surprised that it's not conserving energy because like as I said, we expect to conserve mass and not energy. At least energy only conserved to time truncation. Okay, so challenges for IMEX methods. I'm going to run out of time without getting to anything else. They look promising. However, as I said to you before, if you have a small, say a small grid, a small element somewhere in your grid, that's going to dictate your time step. So these are great methods, but I think they need a little bit of help. And that's what the rest of the talk was about. So for example, let's say you wanted to use what's called extrapolation methods. These methods is basically, it's kind of hard to describe them unless I show you the equations. But basically, think of it as a substepping method, whereas every time you do an extra substep, you're actually increasing the order of accuracy. And let's see if I can show you. Yeah, so it's based on rational polynomial approach for, it uses Richardson extrapolation. So maybe let me get to that. So here's how extrapolation methods work. Again, this looks like a Boucher tableau. It's similar, and these T's come from this Aitken-Naval interpolation. They're just rational polynomial interpolations. And the idea is the following, right? So imagine if you wanted to step from here to here in one delta T, and you had a base method that's of order P. Then what if you broke up this domain and did 2 steps of delta T divided by 2? Then you get another set of approximations. These guys now, if you work it out right using this formula, your method now went from P to P plus 1 doing these 2 guys. You're actually not throwing this away, you're adding all this stuff together, and you're trying to remove the error. And so you go to another set of stages, and now your method goes up to P plus 2. And in the end, what happens is your method looks something like this. The order of your method looks like P plus K minus 1, where K is the number of iterations that I'm showing you here, and P is the order of your base method. Okay, now it's easier to explain. In this case here, I'm showing you an extrapolate explicit method. Basically, the way you do it is you say that your solution at n plus 1 is some solution at some small delta T plus some extrapolation. If this error is not good enough, you go through it again. So it's very iterative, it's recursive. So in many ways, it's kind of hard to call it an explicit method because when you look at the computational cost, it looks a lot like an implicit explicit method because this step here is almost analogous to solving your problem with iterative solver. You're doing a lot of computations. Okay. So far, I've only talked to you about single rate methods, meaning that if you're trying to solve this domain, you have a delta x that's big here, one that's small over here, and say your delta t, which is in the vertical direction here, is all the same size. Well, if you have a small cell here, this is going to kill you unless you make the time step smaller. It'll blow up. Okay, now in contrast, multi-rate methods say the following. They say, okay, these cells here are smaller, so let's make the time step, instead of being delta t, let's make the time step delta t divided by 2. Right, and let's see, and then the issue with this problem is going to be, how do we go from, let's go back one more here. So you start at Tn, you know everything here, everything's fine, right? And you go up to this value, oops, I went the wrong way. When you go to this value here, you're still good. But then the problem is, I now have to go from here to here, right? And I don't know some of these intermediate values. For example, maybe over here, if I have a larger element, how do I get from here to here? These guys, I have them here. And the problem always lies with these multi-rate methods is, what do you do with these intermediate stage values or time level values? How do you get them? Well, fortunately, there's a paper by Constantinescu and Sandu, and then there's actually some work by Bruno Seni and his colleagues in Louvain-la-Neuve that have shown how to do this quite nicely. And here's if I have 4 minutes, I'll finish this up, how these methods work. So you start off with a base method. Let's say we're using an RK2 method, and the tableau looks like this for RK2, right? And in fact, one of the nice things about this RK2 method is that it has this SSP property. And all SSP really means is that if you write the method the way you normally see it in the textbook, right, it looks something like this. But then if you rewrite it as a series of Euler steps, so this E here, delta t means it's a forward Euler step, you can write this method as a series of forward Euler steps and then do a linear combination of them. That's what SSP means. That's it. And
Convex.
so, huh?
Convex combination.
Convex combination. Yeah.
It has to be more linear, it has to be convex.
Okay, it has to be convex. That's right.
Minor.
Right. No, I understood. Okay, so then here's how you do it. If you have, let's assume we have three domains. We have a domain that's coarse, we have a domain that's fine, and a domain that's coarse again. Then the idea is, okay, the problem is going to be at these interfaces, and you'll see that in a minute. One thing that you find is that, again, if you start off with the base method, it looks something like this. The buffer method, this is again by in the paper of Constantinescu and Sandu, the buffer method looks something like this, and then this is the fine grid method here. So in other words, once you get far into the coarse method, you just use the base method, you use this method here. And here, the fine method, you use in this region here, and then only at these interfaces is where you have to do something special, which is this buffer method here. And fortunately, this has been worked out. It's not trivial to work it out, and certainly we didn't do it, someone else did it, but working it out for other methods is not so trivial. And then the way this works is now you have this, so this is that interface between the coarse and fine regions where that buffer method is used. And one of the things, if you're using, for example, a finite difference method, then the length of this buffer region can get big, and it'll actually depend on the order of the finite difference stencil. And so in my student master's thesis, he actually did this with fourth order finite differences. But the work in Seni and Bruno Seni et al., they show that this buffer region spans only 2 elements in DG. Okay, so then here's the problem. The problem is going to be, and you see there's a lot of bookkeeping involved here. You have a coarse grid solve, you have a fine grid solve, and then you have the interface region here. And here's the buffers here that you have to take care of. You have to know what that buffer is. And let's see, let me just get to the end here. And then finally, once you have you solve the coarse, you solve the fine, it has to know something about the coarse. That's where the buffers kick in. And so it becomes very convoluted, as you can see. If you have, for example, a variable resolution grid that's never going to change, it's a lot easier to do. If you have an adaptive method, it's still it's still very painful, because if you look at these interface regions, here's what I was talking about. Let's say you're using a fourth order finite difference method. So you're at this point here, you want to find the derivative here. You need to go, say, 2 cells in this direction to the coarse solve, and then 2 cells into the fine region here. So there's quite a bit of bookkeeping. My student actually did this with finite differences, and it wasn't. We were trying to figure out how we would do it with an adaptive method. We only did a variable resolution static mesh. So closing thoughts, I have no answers, just questions. Non-uniform time-stepping methods appear like a good choice for AMR, static and dynamic. Extrapolation methods, I think, are great, because one of the issues that you have with all these non-uniform time-stepping methods is the synchronization between elements. So for example, if you have 2 elements and they're using different time steps, how do you synchronize them, right? That's the issue. One of the nice things we like about extrapolation methods, if we've only done these for purely explicit, is that synchronization comes for free. You always have it. That's the beauty of an extrapolation method. And it just means that, I guess the one negative that I didn't put up here that I thought about this morning is that what happens, though, is that if you don't know how many of these time steps every cell is going to do, how do you balance your workload in a parallel computer? Like, say, for example, you have one processor that has a lot of these fine grids, right? Or some processes going there that's really fast. Then you have one processor that's doing a lot of work, and the other guys, maybe you're done. That's the one issue that I really see with extrapolation. But the idea of parallelizing extrapolation methods is pretty straightforward. In terms of multi-red methods, the biggest challenge I see there is that deriving explicit RK2 methods is already difficult enough. I didn't show you my master's students' thesis slides, but they're just really convoluted. And trying to extend this to more sophisticated IMEX methods is going to be a daunting task, but perhaps it's worth it. So the question is, can these methods be made to work efficiently? If you look in the literature, you actually see that there are some groups that have had quite a bit of success. Oswald Knott et al., my student with advection, and then the group from Levin-Laneur for shallow water equations, they show that they get quite a big speed up with these multi-rate methods. So it's something worth looking at, but it is quite daunting to do this certainly for an AMR application. Thanks, that's all I got.
Thank you for a very concise talk. And lots in it. Any questions?
In the multi-rate example you showed, can you always do that for any scheme, or you said you know how to do it for RK2?
Right.
For any RK scheme?
You can do it.
It can be done.
It can be done. It's quite convoluted. Bruno.
I just have to say that actually you can use whatever explicit real-time method you want, but with the method that Konstantinos could propose, actually you lose the order accuracy at the buffer regions, but you have a maximum second order. So if you use a classical RK for 4 methods, then you will globally you will only have second order of accuracy, because you lose that at the interface between at the buffer regions. And secondly, for DG methods and for finite volumes, you need these buffer regions to be as large as the number of stages actually that you have in your explicit basis.
Oh, okay.
Actually, it's not only 2.
Right.
It's it's the same number of elements as the number of stages that you have in your base method. Because actually,
that makes sense.
It's the region of influence that you have.
Right.
And so if you use this method with continuous finite elements, there your elements are connected by nodes. So this would extend to larger regions for the buffer element.
Right.
And even the mass matrix and everything in continuous finite elements is for this multi-rate strategy is not really clear.
You're really frightening us.
Yeah. Yeah. So DG sounds more tractable.
Yeah.
So in your opinion, have you guys tried with CG or only DG?
No, only with DG.
Yeah. I can see that. Yeah.
So for this load balancing problem, I'm not sure it's that bad, because if you're doing AMR, you've presumably got some sort of dynamic load balance anyway. So it's just a question of working out what the performance model that you're supposed to be load balancing is.
That's
And
true.
presumably you can actually, because you're dynamically load balancing, presumably you can do a profile guided performance model, which is to say that processors can observe that they are waiting.
So I agree with you. If you only use multi-rate in that setting right now, the way multi-rate extrapolation methods. Extrapolation methods, the way they've been used in the past, is really not for AMR. It's basically for solving ODEs, right?
Mm-hmm.
And the idea is that depending on what is happening physically in a certain part of the domain is when these different number of multi-steps kick in, right? But if you turn that off and you say, I only want to do extrapolation. In other words, I want to let the number of multi-steps be commensurate with the size of your cell, right? Or inversely proportional. Then I see that, because the domain decomposition that you do, if you do it in terms of based on the physical grid, which is what you're doing, you're not doing it based on the physical process.
Well, but no, I'm claiming you're doing it based on a performance model. And so the performance model, if you just take number of grid cells as your performance model, then I agree you have a problem. But you can weight your grid cells. Now the next question is, okay, how do you weight your grid cells? And the answer is, if you're conducting an adaptive simulation as you run along, then you can form some sort of performance model where you weight your grid cells by observation as you run along. And so therefore you might start off with that rubbish load balance, but if you can get that process right, then you should get to the point where your model has a sufficiently good performance model such that it can tell what the correct load balance is by weighting the...
It's good. It's a good thought.
I think so this afternoon I'll be giving a yet another take on IMEX methods, and then we'll have a discussion. Everyone's most welcome to come to one or the other, either just my talk or just the discussion. So look forward to seeing you this afternoon. Thank you again.
Thank you. Thanks, Dale.